Hello, Math 1224. This is Dr. P with Lesson Launch 3-03, an unfinished product. I have a question for you. Suppose I gave you the integral that you see on this screen, the integral of x times e to the 3x dx. What would be your first guess about how to integrate that function, about how to find its antiderivative? I know that when I first took calculus, the first thing that I wanted to do was I wanted to think of this thing as being composed of two different pieces, x times e to the 3x, and then move that over, and then take the antiderivative of each piece. And call it a day. But then my teacher pointed out to me, well, look at this. You think that's going to be an antiderivative of what you see over there? Try taking the derivative of that, and I tried taking the derivative of that. And I realized that because this is a product, I had to use the product rule. And from there I realized that the derivative of this thing is going to be much more complicated than what I have over here. So I don't think that's going to work. So, question is, how do we find the antiderivative of something like x times e to the 3x dx? Well, let's try this again. So suppose I want to take the antiderivative of x times e to the 3x dx. Now it seems like what got in my way previously was that there is this product rule for derivatives, and that product rule makes things much more complicated than I expect when I take a derivative. So if I want to succeed here, I'm going to need to think a little bit about what would be a product rule for antiderivatives. Now the thing to keep in mind here is that every rule about integrals is related to some corresponding rule about derivatives. So you can't think about a product rule for antiderivatives without thinking about a product rule for derivatives. And you probably already know the product rule for derivatives. That product rule is that if I take the derivative of a product of two functions, f of x times g of x, that derivative is going to be the derivative of that first part times the second part, move over a little bit here, plus the first part times the derivative of the second part. So if I don't have all of these things accounted for, then I'm not going to be able to come up with a valid product rule for antiderivatives. Now here's another way of writing the rule that I just wrote down. That's the product rule for derivatives. But if I want a product rule for antiderivatives, then I could say this. I know that the derivative of this is equal to this entire thing here. So another way of saying that is that this function here is an antiderivative for all of this. So in other words, the integral of f prime of x gx plus f of x times g prime of x, the antiderivative of all of that with respect to x is f of x times g of x, plus c. And that's going to be the basis for the integration strategy that I'm about to talk about here. Now, one thing that we can do with this is we can actually break this up into two integrals. We can say the integral of f prime at x g of x dx plus the integral, let me make that a little bit, neaten that up a bit, plus the integral of f of x g prime of x dx is equal to f of x g of x plus c. So in other words, if I could, let me zoom out a bit here. If I could take that integral of that product that I started with and put it in this form, where it's equal to, where the integrand is equal to f of x times g prime of x, where f and g are some functions, then I could say that the integral of f of x g prime of x dx is equal to f of x times g of x minus the integral of f prime at x, g of x, dx. And I'm leaving off that constant for now because on each side of this equation I have an indefinite integral. Each of these is assumed to contain some constant anyway, so I don't need to worry about writing it just at this particular moment. Anyway, by the way, we usually write this a little bit more succinctly. We don't usually write f of x, g of x here, f of x, g of x there. Instead of doing that, we write that. Let me switch colors here. There we go. Instead, we replace the letters f and g with u and v, and then g prime becomes a dv and f prime becomes a du. So we instead write that the integral of u dv is equal to u times v minus the integral of du times v. And that is more typically written uv minus the integral of v du. So what we have here is the fundamental formula used in the technique of integration by parts. And this is a very useful strategy, in fact the most useful one, for integrating a product. So let's see how this plays out in the case of the particular example I gave earlier, that x times e to the x. So suppose I want to integrate x times e to the 3x dx. So what I'm going to try and do here is I'm going to try and find some way of framing this integrand here as u times dv. And there's some strategy involved here, which I'm going to get into probably in class. But I need to pick u and v somewhat strategically here, or u and dv. So I need to pick, first of all, so that I can write down what all of these things are, u and du, v and dv, because all of those things come into play in this formula here. I'm going to need to know all four of those. So just on a blind whim here, I'm going to say let's let u equal to x, and that makes du equal to dx. And let's let v equal, well, actually I don't know what I want v to be yet, because I know what I want dv to be. I know I want dv to be this entire thing here, that e to the 3x dx. And then I need to be a little bit picky about what v is because it's related to dv. I need dv to be the derivative with respect to x of whatever v is. So that's going to force v to be 1/3 e to the 3x. Remember that those u's and du's and v's and dv's always have to be linked to each other. Anyway, if I use the integration by parts formula on this, I'm going to shrink this a little bit so that we can see what we're doing here. There we go. So if I use the integration by parts formula, I get the integral of u dv equals uv minus the integral of v du. And now I'm just going to pull in all of these things over here, all of these, and see what that tells me in this particular case. So that's going to tell me that the integral of x e to the 3x dx is equal to u times v, that in this case is x times 1/3 e to the 3x, minus the integral of v du. That's going to be the integral of, let's see, v was 1/3 e to the 3x, and then du was dx. And now I look at that and I say, okay, that looks awfully complicated, but it's actually an improvement. This is something that at first I had no idea how to integrate except to use the bad product rule, which I tried at the beginning of this presentation. But this is something that's just known. It's just 1/3 x e to the 3x. I don't need to integrate that any further. And this is actually something that I know how to integrate. It has no x attached to it anymore. It's just 1/3 times e to the 3x. So that is equal to 1/3 x e to the 3x minus, and then the antiderivative of 1/3 e to the 3x is going to be 1/9 e to the, ooh, that was ugly, e to the 3x plus c. And now I really do need that plus c there because I don't have any indefinite integral sign on the right-hand side. So I think, if I've done all my work correctly, that the integral of x e to the 3x with respect to x is this monstrosity, which probably wouldn't have been our first guess if we'd been blindly guessing here. But it turns out if you take the derivative of all that, here's just a brief narrative of what's going to happen. I'm not going to go through all the steps, but if you take the derivative of this, by the product rule, you're going to get two parts, one of which is exactly this thing, and then the other part is going to cancel out the derivative of this. It actually works out very elegantly, and I encourage you to try working it out. I'm just not going to do all of that here. But anyway, that was a demonstration of the technique of integration by parts. Again, sufficiently important that I should write it one more time. Integration by parts. And the key step of the whole thing, really there's two main elements here. One of them is we need to know this formula really well, forwards and backwards. And remember, that just comes from something that you've known for quite some time, which is the product rule. It's just the integral version of the product rule for derivatives. And then once you know that, it's mostly a matter of picking these things very strategically, picking u and v, so that the integral that you're given is u times dv, and so that this v times du is something that you know how to integrate, or could integrate by parts by performing another step. And we'll do some examples where you have to do integration by parts more than once later on. But that is the classic example of where integration by parts becomes useful, and I think I'll wrap this up there.